So today we're going to start on the things we understand less well. Okay? So all of the things you've seen up till now are things that we have taught many times.
Except for that one thing.
Yeah, but we've taught many times at MIT at various levels, some of it to freshmen and some of it to graduate students. But today we want to talk a bit about some new ideas that are mixtures, of course, always of old ideas. I'm going to start out with a little bit of the problems of backtracking because that's where we were in last time. Okay, and so we ended with last time, I suppose. We were talking about systems that allow us to do various kinds of search and merge search in with other kinds of computation. There was a feeping creature.
That's me.
Oh, okay. That's what woke you up so you could move that, right? Okay. Okay. Anyway, there is the kind of search of backtracking and search we were doing in the AMB interpreter that I showed yesterday, or both of those that you showed yesterday, were basically chronological backtracking. And chronological backtracking means that you make some decisions in some order, and then you undo them in reverse chronological order the way we made them. So, for example, if this is some sort of search space that you see up here, then there's so this is a tree, and what you have here is a choice which we'll call A, which could be either plus or minus, and then there's a second choice B, which is either plus or minus, and a choice C, which is either plus or minus. Then it is possible that we could say that, well, this may be contradictory. If you ever have the assumption, if you ever make the choice plus A and the choice plus B, then you can't get any further. But you may not be able to know that until you've gone to the end of the calculation, okay? So you've gone to the leaves of this tree, okay? And also, maybe this is a creeping creature, okay? And similarly, minus A and plus C may be contradictory. And as a consequence of those two constraints, the only possible acceptable answers are this branch, and 11 and 14. Okay? And these are the possibilities. Now, this thing happens in some order, and we could say what kind of orders there are. So just to model this, we got some sort of, whoops, that's the wrong model. Just to model this, we sometimes have some code to just fool around so we can see what's going on. So here's this tree, the tree that you just saw. Okay, these are some record type for the record type for the tree nodes. They have a left and a right value and a current value at that node. And here's actually the representation of that tree in a nice. Syntax doesn't matter very much. And let's say we walk this in the call by value order, that is the applicative order. Okay? So this is the order we're going to walk it in. We're just printing it out so we can see what that looks like, and it goes out in that order. Which, by the way, if we go back to the picture over here, what we see is that that's the order you would expect. Okay, for a depth first search, you do this. Then you come up here and do this, okay? And this is the order of examination of things, okay? And then you go down this path, okay? And so there's sort of a path that's the one that's the natural path you expect, and every time you see a new node, you write that down, okay? Now, if we worried about actually solving this problem. Oh, that's interesting. It's not that nice, huh? Let's see, how do I grab this? Can I grab it? Growl. Oh, I see. Goes way down there. The scroll bar here? No, the scroll bar doesn't work. You see, it only allows me to go. It won't let me go up.
No, that's not the scroll bar. Anyway, go on.
Oh, is there a scroll bar here? No, I don't see one.
Change the-
I will. Calm down. Yeah.
I'm
Boom.
telling you to ignore me and do it.
Okay. Yeah. Okay. So there it is. Okay, and now I'm going to make this smaller so that it will fit. Good. Yeah. Okay. So this is the same. This is a program that's actually one implemented with AMB, just to see what the same phenomenon going on. But every time we actually hit one of the nodes that's okay, that's acceptable, this program will write out a star followed by that placed in the tree. Okay. So you want to see the walk and see how it happens, and then see when we encounter the goodies, the things that we're interested in. Okay, and so under those circumstances, we see that indeed it's happening in the order we expect. Okay, and you might imagine that if we didn't call by name order, it would be different, but it isn't. Believe it or not. Okay, strangely enough. Okay, so this is a problem, and the reason why it's a problem is because this kind of search doesn't learn anything from having done it. Well, the searcher doesn't learn anything from having made mistakes in the search. So, for example, having walked down this path and discovered that A and B by itself, if we actually had those words at all, you see, if we had the words A and B are together a contradictory, which we may not know. That's an implicit constraint in the computation we're doing. If we could figure out at that point that that was true when we got down to here, then we know we never have to look at this. Okay? Or if we figure out that A and C are mutually contradictory here, not A and C are mutually contradictory here, then we know we never have to look down this path either. You see? So the things that we know we don't have to do. So is it possible to make use of the information we can pull out of analysis of the errors we make? Okay? How do we learn from our mistakes? Now that's a real problem, and just want to discuss before going any further. What are the reasons why people mostly make things like depth first searches? Okay? Almost all the searches you ever see are depth first and chronological. Okay? And the reason, of course, is because it's easy. It fits the structure of your language. Okay? It has certain clear advantages. It's amazingly easy to implement. Okay? It's got reasonably good machine efficiency because it fits into the structure of the computer language you're dealing with, or that sort of thing. It's noticed that it was only implemented, in order to implement it, was only a small perturbation of the basic evaluator algorithms we did last time. It really was a small perturbation. Okay, so that makes it even easy to build it into the language. So not surprising, for example, that Prolog does it that way. Okay? It's easy to understand how it works. That's another important thing. Okay? It's, left branching, depth first searches is pretty clear what's going on. Breadth first sometimes is a little harder. And by the way, although it's guaranteed breadth first, guaranteed you get the best answer, it has the problem that it may do a lot more work to get to that answer, because it has to look at a lot more stuff if there's a wide tree. Okay, so it does, but the crucial thing is it doesn't undermine the expression-oriented structure of your language. See, for every it might be true that for every choice point, it's possible to order the possibilities to make the choices in some good order, but that's a different question from whether or not there's a way of actually choosing which choice point to work at. Okay? You see, what you'd really like, instead of this kind of a structure, is you'd like something that looks like this. Minus A, minus B plus B, minus C plus C, and you'd say, well, what are these are independent choice points, really. There's no order to them. Okay? And I might want to make some deductions based on these, and sometimes I get little contradictions, and sometimes I don't. Okay? But these things, then I can attribute somehow which choices are the ones that cause trouble, and which choice points have to be tweaked. Okay? Now that's something that's got some long history. People have spent a lot of time on this. There are SAT solvers and wonderful things like that, and we're going to talk a bit about that today. Okay? But the crucial, I want to sort of walk around this idea a little bit more. How can we be more clever? Okay? And we have to be, because searches are intrinsically terrible. They're intrinsically exponential. Okay? And it's also the case that if you have some extremely complicated computation that occurs, as the kind that I'm interested in when I worry about things like physics or electrical circuits, and I drew it last time, I said, supposing it's the case that I had some process which was a generate and a test and something complicated in between, some function that computes something like the orbits of a space probe. Okay, I'm trying to figure out what's a good trajectory by trying to generate appropriate possibilities. If this is enormously expensive, then that's what dominates the computation, not actually the exponential behavior of the search. Okay? It might be that you only look at a few possibilities, but each one takes a very large amount of work. Okay, so that means there's constant factors that might be very valuable to eat up. So how can we be more clever? First question, how can we learn from our adventures when we do searches? Okay, that's interesting. Yeah, how do we figure out what we're doing when we hit dead ends? Okay. And the important thing is that we need some ways to assign blame. We have to have a way of saying, why is it that we hit a contradiction? Okay? And once we have to do that, we have to be able to recognize the situations that we're considering and see whether we're getting into them again. That's another problem. Okay? We have to have control structures that allow us to cut off pieces of the search so that we never have to go near those places. Okay? And what we need is to be able to reuse the results of computations that are not affected by a contradiction we discover. That's very, very hard. Okay?
Barry,
Yes, sir.
You point out that the topic you're talking about now is kind of also the meta topic for the whole class. So we have this nice reflection.
Yes, of course. Okay. Yes. Okay. So right. So for example, okay, if I'm in running this program, I do some nice deduction based on minus A and minus B and say minus C. Okay, and I learn lots of stuff, and then there's some contradiction I get into that doesn't involve those. There's no reason why I should ever lose any information from that or ever have to recompute any of that. That's a hard thing to do. Okay. So this is a rather interesting problem, and now what do we need to be able to do? We have to have some ideas. Now that I've told you the goal. Okay? Well, to be able to assign blame, we have to know which assumptions or choices we make that lead to the results we get. Which means we have to have names for them. We have to have at least something we can grab onto. A choice has to have a name. That's an interesting thing in itself. Okay? You can't, if you're every sorcerer will tell you if you have the name of a spirit, you have power over it. Okay? And of course, computer programmers are sorcerers, from the point of view of the inside the computer, at least. Okay? So we have to have names for those choices. We have to also be able to, when we assign blame, what it means is we have to carry the choices along with the values that we produce. So we have to have lists, perhaps, of the choices that come as part of each value. Okay? That means we have to sort of carry them through the computations the way we carry other things. So if I add two numbers together and one of them comes from Joe told me so, and another one comes from Harry told me so, and I take the sum, then the sum depends upon both Joe and Harry. That's an important thing to know. So I need that information. Okay? And that has an added advantage. It has the advantage that if you have that somehow, then you can answer questions like, why do you believe this? A lot of this came from teaching, by the way, that I'll get into in a minute. In fact, Richard Stallman and I, in 1975, when he was a freshman at Harvard, and I hired him to work for me in the AI lab at MIT, Richard Stallman and I I was worrying about teaching. Actually, I was teaching the introductory electrical circuits class. Okay, very interesting class, and most of the time we tell people lots of equations and things, and the students look very glassy-eyed. And because the reason is because actually very serious engineers don't look at those equations. Okay, I'll be more clear about that. I mean, what is it that's an introductory electrical circuits class, just to give you a feeling for it for those of you who've forgotten all this stuff. Where did I put my eraser? Oh, there it is. How did it get there? Huh. Right. Poltergeist, right? Poltergeist. Okay, so what there are in the electrical world, it's a kind of language, and I'm just going to give you the quick summary for 5 seconds, is there are things like this, which are little boxes, okay, which have variables on them called voltage and a current, and associated with a place like this is a potential, E1 and E2, and that these are numbers that have to do with physics. Okay, and you say things like, well, V equals E1 minus E2. There's a current going in here, I2, I1 plus I2 equals 0, and V equals I1 times the resistance, V. Okay, so this is the specification of this part. Very simple. Okay, it's a very simple sort of thing. You connect these things together, things like this, and there are many kinds of parts like this. And you connect things together by saying, well, if I've got something like this, then that is the potential at that point, is the same for all of the things that are connected. Okay? And the sum of the currents going into that place is 0. I1, I2, I3, I1 plus I2 plus I3 equals 0. So that's Mr. Kirchhoff's laws. Okay? Two simple, very simple phenomena. There are some complicated things. There are things like this, you know, that say this has a voltage, V, and a current, I, and it says that the current is some constant dependent upon the physics times the device, the geometry of the device, times e to the q times the V over Boltzmann's constant times the absolute temperature minus 1. So this is some physics. This is a physical. This is the charge on an electron divided by Boltzmann's constant times the absolute temperature. Okay, and this is something about the geometry of the device. But that's a complicated law. Okay, and it has a very similar behavior to something like that, except for that the constituent part of the law is complicated. Okay, so there's all sorts of things like that. And you know, everything looks very simple, except for the fact that when you put 100 of these things together, some of which are nonlinear like this, it's a mess. Okay, and you know, so if you teach students all sorts of clever tricks for manipulating small combinations of them, well, they may get some insight into the matter, but they're basically thinking that what this is a manipulation of algebra exercise. Okay, now this is of course not at all what a real engineer does. Okay, and so I had observed from by watching an actually very, very good engineer, Paul Penfield, how he actually does it. Okay? He was teaching this class also with me, and he was a much older man. And so I observed what he does, and I said, gee, why can't we teach the students this? Okay? And it turns out, of course, the reason is because the kinds of methods we teach students are the ones that fit on one page of or 5 pages in natural language in a textbook. Things like the node method, or remember that? The loop method. Okay, right. Those are all things that can fit in 1 or 2 pages of a textbook, okay, written in natural language. But the algorithms that are run by somebody like Mr. Penfield are themselves much more complicated, but much more easy to execute. Okay, so that's the sort of thing you'd want to teach a student to be able to do, because that's how you teach them to be an expert like Mr. Penfield. So having observed this, I started trying to formulate this material, and I got Mr. Stallman to help me with this. We sat down, and I wrote part of the program, which I called a propagator, and he wrote some algebra for me that did manipulations of algebraic expressions, because you need to do some algebra. Let me just show you what propagation is like, and we'll get into that today. Okay? So this is what is this? This is a lo-fi amplifier. Okay? You might find it in the quote old-fashioned transistor radio, right? For your when transistor radios had 8 transistors. Okay, so this is a lo-fi audio amplifier. It has 4 transistors in it, each of which is running in the active linear region. I'll say words that you don't know. If you don't know, it doesn't matter. Watch about how I think. Okay? It's interesting is the thinking. Okay? Signals come in here and go out here. This is a power supply from here to here. But the important thing is that I'm going to do some analysis, and I'm going to do this by first finding out the DC bias conditions. And then I'm going to see how the incremental analysis works as a consequence of that. Okay? So the DC bias conditions, in those cases, the capacitors aren't there. They're just opens. Okay? And what do I see here is I see that there's a voltage divider. Okay, so I'm looking at sort of I've got a little tube, and I'm doing matching. Okay? I'm matching little regions of this. I say there's a voltage divider here. And the voltage divider has the property that the voltage here is known if I know the voltage here and the voltage here. It's RB2 over RB1 plus RB2, and that would be the voltage here. Okay? Assuming that no current is going this way, which is a reasonable thing to assume for a transistor in the active linear region. Because the current through a transistor going this way is about 100 times the current going that way. Okay? It's called beta, that number. Okay? So, and this is set up, by the way, so that I got beta squared, so it's 10,000. Okay? But we'll worry about that in a second. Okay? So if I know that this is the voltage here, which I just deduced, then I know that the voltage here is 0.6 volts below that. That's a property of the transistor, assuming it's in that region. So I know the voltage here. But since I know that, then I know the voltage here is 0.6 volts below that. So I know the voltage here. If I know the voltage here, and I know the voltage here is 0, because that's what this means, then I know the current through here. Okay? Oh, but that current must be coming this way, because it can't come in there, because that's 0, basically. Okay? So it must be coming this way. It can't be going this way, because that would get 0, and it can't be going this way, so it must be coming through that resistor. Okay? So therefore I have I know the current, I know the voltage up here, therefore I know the voltage here, using the little laws that are written over here. Okay? So I've done deductions that are all based on very low local observation. I'm looking through a tube, and each of these is a little machine, as I'm seeing, or my mind is thinking of a little machine that's obeying or dealing with the local behavior around it. Okay? So now that I know the voltage here, well, I know the voltage here is 0.6 volts below that. These are 2 resistors in series because this isn't here. Okay? And as a consequence, I know the resistance, and therefore I know the current through here. So I know the current through here, so I know the voltage here, so I know the voltage here, so I know the current through here. So I know all the currents and voltages in this circuit in the DC bias analysis. Now I have to make sure that this is right. Okay? Because what I've done is made lots of assumptions. One of the assumptions is the factor of 100 didn't matter. You know, that those base currents were too small to matter, that they wouldn't affect anything. And the other assumptions are the states of the transistors. The transistors could be active linear, they could be saturated, they could cut off, something like that, in which case they have different behavior in those regions. Those are almost like a switch. Okay, so if I say, well, since I knew the current through here and it went this way, and I know that was something like maybe a milliampere, that means this is about 1/100th of a milliampere, which means it's about a 10,000th of a milliampere. Would 10,000th of a milliampere make any difference to the voltage I deduced there? Okay? I have to say, well, I'd have to recompute this little voltage divider and find out and say, oh yes, it moves it by about maybe a 1,000th of a volt, a millivolt. And if it moves it by a millivolt, then this only moves by a millivolt, and this moves only by a millivolt, and therefore this moves hardly any at all. Okay? And therefore this didn't matter. It didn't change the state of the transistor as I deduced it. And I have to check all of those conditions. Okay? So that's the DC bias analysis. Now, once I've done the DC bias analysis, this tells me about the incremental properties of the system. Okay? I now am about to do differencing around that. I say, oh yes, well, I put a signal in here. Now this is a short circuit, and so is this for incremental analysis. Okay? If I tweak this voltage up a little, then this goes up the same amount, this goes up by the same amount, this goes down by an amount, which is the ratio of this resistor to this resistor. Okay? Therefore, I know the gain of this stage is the ratio of RC1 to RE1. Okay? But if I tweak this down, then this goes up by the amount which is the ratio of this resistor to this resistor, because this place is incremental ground. Okay? And so therefore I know the gain of this stage. And this one's a unity gain stage, because if I move this voltage, this moves up by the same amount. Okay? So now I know that the gain of this, the voltage gain of this amplifier is RC2 over RE2A times RC1 over RE1. I've just done the analysis that would take a freshman a week, okay, and probably not get it done, okay, and there'd be exponential equations and all sorts of nonsense, which is based on the fact that we're telling them the primitive algorithm but that works with the general case. Okay, I'm showing you the special algorithm that's used by an expert. Okay, so that was the intention at the time, and Stallman and I actually produced such a program, okay, which had lots of interesting, fun properties, one of which is that if you asked it the question, why do you think the voltage is what it is, it could spit out the answer because it had the argument, because in fact it had attribution, it carried with it the attribution of which parameters were dependent upon for each value that you deduced. Okay? So this is sort of a teaching aid, but mostly it was a teaching aid for me. Okay? And in the long run, it motivated the introductory class in computer science, 6001, because the idea of that was to teach people how to program in such a way that they learned how to think of it as a language for expressing themselves. Because once you can learn how to program, then I could give you the program, which is only about 5 pages of something like Scheme, that does what I just said, and you could read it and say, oh, I see how to do that. Okay? So a program is as much for a person to read as for a computer to execute. Okay, now the reason why I got into that is because there was one other thing that we discovered at that time. About a year later, Stallman and I discovered that, well, you know, we don't really know the states of these transistors ahead of time. They could have, each one may have 3 possible states, okay, and that means there's a combinatorics there, and if I had something with 100 transistors, I'd be in real trouble. But most of the time, systems are isolated in DC, so whatever this is connected to, it doesn't really interact with it. So this really, this subsystem only has 4 transistors that are relevant, so there's only 3 to the 4th possibilities. And gee, if I could do the search for that little local region, and I do the search for the other little local region that's isolated from it and so on, then I could probably deal with very large circuits. Okay? And so we invented a means of tracking the dependencies and using them to determine the states of the system as a whole, okay, rather simply. But of course, to verify whether a state is correct or not is a big computation. It might involve solving algebraic equations, because in this case there was no feedback. If there's a little feedback, I'd have to have at least one algebraic equation for each feedback loop, and things like that. And so that was the sort of problem that you know, by golly, I didn't really care about the exponential search other than cutting it down enough so that and being able to use the real cost was the algebra at the time for each case that I wanted to consider. So we introduced that around that time, and then I suppose we call that dependency-directed backtracking. That was what we called it at the time. And I suppose then my former students, Doyle and McAllister, separated that out to make a truth maintenance system idea, which many of you may know about. And then Forbes and DeClear systematized that in some book that everybody knows probably, called How to Make Problem Solvers or something. And Guy Steele developed a constrained propagator language as part of his PhD thesis work at MIT. However, the real question is, can we generalize this to arbitrary programming? That's what we're going to talk about today. Okay? Generalize this kind of idea to arbitrary programming. And indeed, some people have made some advances in that direction. There was Ramin Zabeh way back around 1980, I suppose. David Chapman and David McAllister also tried to merge dependency-directed backtracking into an ordinary language like Scheme, and made some progress, but it wasn't very effective and certainly never caught on. And there are reasons why it wasn't effective. And so we made a lot of progress recently, and I'll tell you more about that. Okay? So really what is the problem? Why is this hard? And the reason it's hard is we have an expression-oriented language. And almost all of our languages are expression-oriented. And expression-oriented means that there are values that come out of expressions. Okay? An expression is some sort of tree structure, not the one you saw before, unless I start putting pluses in my things on it. But expressions are tree structures, and what happens is that values are put in at the leaf nodes, and they bubble up through the tree, and they come out the top. Okay? And I'll explain why that's a problem. But the main thing is that the expressions induce an order on lots of things. For example, one of the orders is, what's the order of evaluation of the arguments? Or it might be parallel, but it's an order. Okay? It's partial order then. There's you can't compute the contents of a procedure unless you have the appropriate arguments. Even in normal order, you have to get the values of the arguments. So the value of the arguments that are relevant have to be used to produce the value of the result. Okay? That's another ordering constraint. That's real. And it doesn't matter whether it's normal or applicative order. It's just different order, but it's an order. Okay? And so this produces a problem because what you saw, I had a nice set of unordered the choices, and what we saw in the tree was an ordered set of choices. Okay, so there's part of that problem. And what that means is that, of course, if we go back to that tree, which is over here, there's a whole bunch of things that we'd like to be able to do that's not so easy to do. Okay? We need to have means in our language for jumping out of this kind of a disaster. If we are here and we see that B and A are somehow incompatible, we have to get out of here and say, oh, nothing like this will work, I better go down this branch. Okay? I mean, this, of course, could be an arbitrarily complicated branch, you see. And I don't really want to investigate this one that hasn't got a chance of survival. Okay? So I have to be able to jump out, and I have to be able to know where I'm jumping, so I have to have names for those places. Okay? It also has to be the case, again, it's names. Okay? We have to have names. That's the critical thing. We have, in order to have power over spirit, we need the names of the spirit. Okay? Now, in an expression language, if a choice must be revised, also, all the work that was done in making that choice, okay, some of it may be reusable. Okay? So, for example, again, in here, there's a minus A and minus C have some things in common, and they can produce even though the minus A and plus C hurt you, minus A plus B and minus C have some consequences, some of which may be only due to minus A and minus C. Okay? When I get down this path, which is a good one, I don't want to have to recompute any of that stuff. Okay? I want to somehow have some ability to work with this, and so that I preserve all the old values. Some kind of memoization technique. Okay? Now, if we go back and look at that electrical circuit stuff, the reason why this all worked fairly easily there, and it did, and we could do this in 1975 and 1978 and things like that, and it worked just great. Okay? But to make this general, it was hard. Okay? And what's the special thing about the electrical circuit thing? The special thing about the electrical circuit thing is that, first of all, there is a name for every variable. For every value I'd be interested in, there's a name. Okay? The names may not be implicit on the diagram, but they're associated with the geometry. And the geometry is fixed. Okay? So I have places like nodes, and I have little terminals which connect to the nodes, and terminals carry currents and nodes carry potentials. Okay? And so there's associated with this place, there are 5 variables that are interesting. 1 potential and 4 currents, which happen, the 4 currents add up to 0. Okay? But that's a very important thing. It means that there's a name for it. The name is I make use of when I write something on the diagram. The diagram is my memory. and I write on the diagram the little values that are the memoization when I remember what I've done so far. Okay? So that's the key that makes this thing work. Okay? And the problem with expressions, just to be very clear, okay, is if I have something like an expression like the sum of Fibonacci of minus n1 and Fibonacci of minus n2, okay? I don't have a name for this value in this expression.
Well, you have parentheses.
I don't have a name for it that I can access easily, that I can attribute something to, that I can write on. I don't have a place. I personally, as a human, can do this, okay? But as a computer program reflecting on itself, I don't have a name for that. Okay? Certainly at runtime, I don't have a name for it. Okay? So an idea that makes sense is to generalize this. So you think of these as little boxes. Okay? So here's some fib box, and it happens to have an input and an output. Okay? I don't care whether they're in some pattern or not like that, but that associated with this is a little cell. Okay? And we need a different kind of structure here, okay? And this connects to a thing which does a subtraction, minus, which has little cells, okay? So there are little things called propagators, and there are the cells which represent the places where memory is that have names. They may be implicit, but they have names, and they can remember things, okay? And furthermore, you can do lots of stuff with them. So that's a generalization of the idea of expressions, okay? That the expressions are laid out as these little wiring diagrams, which is so successful. But then the problem with real computation is the wiring diagram is not finite. Fibonacci is as big as it needs to be. It's a wiring diagram that grows to fit the problem. It's virtual wiring diagram. It's a big tree of adders and that's it, I suppose. And constants, ultimately. Okay, but because this little node turns itself into another one of these for a different end. Okay, so that's an idea, and it's an important idea, and it's actually the idea that we're going to talk about for the rest of today. Okay? Now, one of the things that's going to happen is that besides the fact that that we're giving names to the outputs of expressions, if you want to think of it that way. Once you do that, you can do further. You can make those expressions have multiple sources. You see, once I'm allowed to hook things like this, I can have something else that puts something in there. Right? Maybe like that. Okay? And what does that mean? Well, we don't know yet. Okay, we're going to tell you about it today, but it's a generalization that may or may not be of value. It turns out it is. And so once you do that, you change the entire nature of the computational infrastructure. And so diagrams of propagators, okay, with cells interconnecting them, become a new kind of infrastructure analogous from the point of view of high-level language to what machine language is for current high-level language. Okay? And that's all I'm going to say until Alexei starts in about 15 minutes. Okay? Alexei's going to tell us about his research on this matter. Okay?
Sure.
Yes, sir.
Mike, in the tree diagram, when you're talking
Yes.
about having to recompute things, I think that actually is a little clearer if you use something like the 5 floors problem.
The 5-floor problem.
5 floors, because
Yes.
they talk about the choices and how they're independent.
Yes.
And how you can determine.
Absolutely.
The tree is bigger, so it's more.
Yes, it's bigger and fluffier, and you can see all the stuff going on. You're absolutely right. So, in fact, what Chris just pointed out is that, for example, in the floors problem, that was from Dinsman's book on puzzles. Okay, there was Baker, Cooper, Fletcher, Miller, and Smith. Okay, and each one could be on the floor, and so there was a let, and it said here Baker, be Amb 1, 2, 3, 4, 5, and Fletcher, et cetera, right? And there was for each of these guys. Okay, and then there were a bunch of constraints that say what things can and cannot be true. Okay? And what's going on here is that, indeed, suppose it's the case that some terrible disaster, supposing these were evaluated in this order, I don't care. Turns out in the MIT scheme they're evaluated in the other order, but it doesn't matter. Okay? Suppose they're evaluated in some order. So there are five choice points, each of which has 5 possible choices too. Right? So there are 5 choice points, and each of which has 5 possible choices. And suppose it's the case that some constraint over here discovers that that the choice made for Baker and Fletcher were inconsistent. In the traditional language that you saw last time, okay, first of all, there's 2 things that go on. One is that it would never know that that was the problem. Okay? It would just know there was an inconsistency, so it would search out all the other possibilities down here before getting back to this place. Boy, is that a waste. Okay? That's what I said about going down this path, this one, okay, for a very long story. Okay? And the other problem is that once it did get a consistent set for Baker and Fletcher, for every possible set it tries here of those 2, it's going to have to go through this whole rigmarole dealing with these again, and then making choices for these, which may or may not be consistent for their own reason. So there's no simple way to jump back to the right place. We don't have a name for it. And there's no simple way to preserve the computations that don't depend upon it. Is that what you want me to say? Okay. You want to say some more? Good. Okay, good. This is why I said today is the day we're talking about things we don't completely understand.
So the model I like to use for this, which is I find very compelling, and maybe some of you will too, I can just use this, is that if you think of this generator here as defining something like a 5-dimensional search space, okay, then you'll have a constraint, something like saying Baker and Fletcher have got to be on adjacent floors, okay? And if you can take advantage of that constraint somehow, then when you discover that those things, that there are combinations of those values that can't work, in effect what you're doing is you're slicing out entire planes of the space and saying, I don't need to look there. You find it out once, and then you just throw away that part of the search space. You can get really aggressive, you can get very aggressive results, where you cut down the search space quickly by a handful of constraints that are very broad, which is very hard to do without knowing why you made some sort of decision. And I think what ends up happening is that people build these things normally, but in an ad hoc way, and we're trying to say, well, you can do this in a very simple way that's independent of a lot of the details of what you're building. Okay? And that's sort of...
So anyway, the reason why, let's go back, the reason why Zaba and McAllister and Chapman stuff didn't quite make it is because, first of all, it didn't quite solve the problem of recomputing, avoiding recomputation, okay, which is a big deal. And the other problem, the other thing that was really very important is that it hadn't made the breakthrough of having multiple sources and what that means. And we'll talk about that today. Okay? So I think we should have a break now for approximately 10 minutes or so. And then we have Alexei, who's going to talk about the research we've been doing recently about this, which is a major portion of his doctoral thesis.